Okay, this lecture is hopefully will be quick, just to show how we get the Schrodinger equation. Now, we've kind of built up here talking about Maxwell's equations, talking about in terms of operators and connecting it to the energy of a photon. This was all kind of a setup for this particular lecture where we quote-unquote derive the Schrodinger equation. Now, there is no formal derivation of it because some of the steps in what we're going to do, there's no formal proof of. But this to say that it's not like the Schrodinger equation came out of thin air. There was a rationale behind it. And again, the difficulty here, let me just quickly kind of come back here. When we look at the difference between classical physics and quantum mechanics, put it up here. We have this differing view. Now, first of all, and again, comparing, let's just say light, or, light, let's just stick with light, and also particles, which we'll concentrate on, say, electrons. The views will be seen to be different. Now, when we talk in classical physics, light is a wave-like phenomena. And again, governed by Maxwell's wave equation, like we said. And so what we've done in this is we've gone over to quantum mechanics and say, oh yeah, so this is now a wave equation for psi. And so there's a natural thing. The new thing, though, what's new, is that now we have light can be seen as particles, photons. That's the new thing. Now, in classical physics, when we talk about electrons, there's particles, right? Newton's equations. So if we were to Newton's laws, I'll say. So if we were to talk about electrons in a classical sense, we would use Newton's laws to describe them, and people attempted to do that. The problem is that when we go to quantum mechanics now, what we did in terms of the photon, we said, okay, there's particles, but it's described by a wave equation. But we know what that wave equation is because we have the classical correspondence, because when we go to many, many photons, we know what light behaves like in terms of Maxwell's wave equation. When we talk about electrons, this connection breaks down, and there's no classical wave equation for an electron, for example. So we have to rely on different methods to obtain the wave equation for an electron. I'll say psi for electron. There's no classical connection to rely on. And that's why we built up this method from Maxwell's wave equation working back to the energy relation to do that here in terms of a particle. Okay, so clear the board, come back. So this is the process we talked about. And I'm going to go relatively quickly here. But remember, we could start with the classical energy. If P is an odd power, we'll multiply it. That won't be a concern for us here. Multiply both sides of the equation by psi, again, and we're going to assume that it's an eigenfunction of energy and momentum, turn it into operator expressions, then write the differential form, and from there. So we begin with the classical energy of an electron. However, we're not going to deal with that. We're going to deal with a time-independent potential function, just to make life easy to start off with. And that can be dealt with if it's a time-dependent potential. But here we are just going to assume it's time-independent for sake of simplicity. So let's begin. Well, we've already done items 1 and 2 by writing down the energy equation. So that's 1 and 2. And now we just multiply both sides by psi. That's step 3, again. And then we note that converts, since the eigenvalue-eigenvector connection here, E psi here is equal to E caret psi, the operator acting upon it. So that just goes straight over to this. like that. And now we stick in the differential form for these. And again, note here that I wrote out p squared here. P squared is minus h, because it's IH bar, we're squaring that, two derivatives with respect to x. And now we can just do a straight substitution. So the e goes directly, well, let's go to the next screen. So e goes directly to this, and p squared becomes minus h bar squared over 2m, second derivative of psi, interacting to the left. And this is it. This is the Schrodinger equation for a non-relativistic object in a one-dimensional potential, and it's also time-independent potential. So that's what we're after here. And so what we want to do is take a look at a small number of examples and just some interesting aspects here and there. So just quickly here, free particle in one dimension. A free particle means there's no potential. So there is no v here, and that's all you get. IH bar partial psi partial t is equal to minus h bar squared over 2m partial, second derivative psi with respect to x. The harmonic oscillator is probably one of the most important quantum examples in all of physics, I would say. It's ubiquitous, it comes in everywhere, and it is a very important one. I would say probably the most important one to understand. There's different ways to solve it, some beautiful ways to solve it, and if you're going to go on to understand string theory, for example, you're going to need to know how to solve the harmonic oscillator, and plus a lot else. Right. And if you go to higher dimensions now, all that happens is we think about going back to the momentum. P squared as a vector is p dot p, which is px squared plus py squared plus pz squared, and as an operator that just becomes the x momentum in the x direction, momentum in the y direction, z direction, which just says that we're going to have this form here. We're going to have these three second derivatives all in a row acting on psi. So that comes down to here. And if you know your multivariable, this is what's called the Laplacian of psi. But this is all you just need to think about. It's just the three partial derivatives in a row. And psi there is going to be a function of position and time as well. Another important one is the hydrogen atom. Of course, we probably won't spend time on this one. It can get rather involved. But at a very basic level, it can take a very simple form here. Minus h bar squared over 2 mu, which is the reduced mass. It has to do with the center of mass of the proton-electron system. So that adjusts for that, essentially. And the potential is just the Coulomb potential, minus k. Again, this is the wave function for the electron. E squared over r, that's the potential the electron sees. Actually, there's a lengthy part of factorizing it in terms of the wave function for the proton and the electron, but really, when you want to talk about the hydrogen atom, you care more about the electron and the state it's in. So there's still stuff to do. This is just, we've just introduced the equation, but we understand what is the significance of the Schrodinger equation. We sort of kind of scratched the surface before, but we know that our wave functions must satisfy it for the system that we're talking about. We'll take a look at the free particle. That's an important one to understand, and the issues related to that. Restrict the equation to what's called the time-independent Schrodinger equation. There's a typo there. Schrodinger equation. And then find the constraints of allowable solutions for the time-independent Schrodinger equation. How to solve that. And that's really kind of the one of the skills to be developed in this course. And develop methods to solve simple 1D problems, and then solve some basic problems. And we'll do that in the further lectures.